Hi, today we're going to be designing a power supply, and this is going to be a power supply for like typical drone, but it's going to have several power rails, like it's going to have 5 volts, 6 volts, 12 volts, and possibly also 19 volts. I'm just going to bring up KiCad. We're going to get started. If you've seen one of the previous videos that I've done, I was actually going to replace a power supply on a different board, and that's still pending, but I also want to kind of try this power supply that I've chosen and see if it's going to work for other applications, and see if it's going to work well for different voltage levels, and just have a way of evaluating it. So what I'm going to do is I'm going to design a board with just maybe 4 power supplies with different voltage levels, and then those are going to be tested on a drone application. So we're going to go to KiCad. Let me just see if I can get this window out here, like this. And then we're going to go to Mouser. See if we can find this power supply. I think it was called LTS, like LTS, what could it be, 53? LTS, let's see, 60 volts or 3 amps buck converter. What was it called? TPS, right, it was called TPS 54362. So the one that is 362, it's probably 3 amps. Here it says 3 amps. But this is not really the one I was looking for. It was actually this one, I think, 54360. Because this one has a bigger package and it has a little bit more stuff in it. But what I want to have is just a simple one. Just one like this. So we'll go ahead and search for just TPS 54360. Okay, so they all come in those TS, like I think it's a TS SOP. It's some kind of SOP package. They don't have any other package, unfortunately. I would have preferred to have DFN or some smaller package, but this is the packages they come in. This one actually says 3.5 amps. Let's open the datasheet and see what it is. So this is a buck converter, and it is designed to work up to 60 volts. Now the application that I'm designing this for is going to be working on 48 volts. So having a little bit of margin is good, and also if I can use the same buck converter for many different applications, I'm just happy about it, because then I can test it thoroughly and make sure that it works in every situation. And also this buck converter has a very good efficiency over the full range, and I like that very much. I like this curve. This curve looks very good. Here's a simple, like simplified example schematic. So it seems to have, let's see, this is probably a sync input to the buck converter. Let's see what it has. Let's see what it says about this input. RT clock. Where is RT clock? RT clock is a resistor timer and an external clock. And an internal amplifier holds this terminal at a fixed voltage when using an external resistor to ground to set switching frequency. If the terminal is pulled above the PLL upper threshold, a mode change occurs and the terminal becomes a synchronization input. The internal amplifier is disabled and the terminal is a high impedance clock input to the internal PLL. If clocking edges stop, the internal amplifier is re-enabled and the operating mode returns to resistor frequency programming. feedback, comparator, the error amplifier output and input to the output switch current comparator. Connect frequency compensation components to this terminal. Let's see, does it have a, can we set a current limit on this one? So absolute maximum ratings, 65 volts. Also, when we set the boot pin here, it's very important that when you choose a capacitor for the boot pin, that it has to be a capacitor that is able to handle the voltages that occur on the boot pin. And in this case, if you look at the voltages on the boot pin, they're always higher than the voltages on the output. And also, like, they're always higher than the voltage on the input. So the whole reason of the boot pin is that it's designed to have a capacitor that is going to bring the voltage on the internal MOSFET gate higher than the input voltage. So if your input voltage is 60 volts, then the value on the boot pin can be 72 volts. So it's usually about 12 volts above the input voltage. So when we pick a capacitor there, we have to pick a capacitor that is probably 80 volts. If we're going to support the 60 volt input. But if we're just going to support 48 volts, then we can pick a capacitor that is 63 volts, for example. So we got a bit of information about ESD ratings, an overview. Is there a current limit? Let's just check if there is a current limit. Current mode, current source, come on. So here it describes some features, and it says that it's supposed to have accurate current limit operation and maximum switching frequency. Okay, so here it describes also that it is important to select switching frequency such that you can maintain the current limit. And here it actually tells you the equation to calculate the maximum switching frequency. I'm going to read all of this in detail later. I'm just looking through this to see if it has a current limit, which it obviously has, but I also want to know how it works. Okay. So it seems to have a fixed current limit set to around 4.5 amps for the output of 3.5 amps. Internal soft start. Which I suppose is it means that it has a delay, slight delay when it starts. So you don't need to have an external capacitor to regulate the start. And it comes in an 8-terminal HSOP with a power pad underneath. Okay, let's build something with this. So let's go back to KiCad and let's see if we have this component first of all. I'm using KiCad 5, so this is like a bleeding edge compiled version that I've built. So some things may not work in this version, but we'll just have to find out. Let's see. They have changed how they handle libraries. So there is a totally different way of handling libraries. Okay. So it seems we don't have any libraries loaded. Let's see, how do we add libraries in KiCad 5? Right. The problem was that I didn't set the environment variable for the libraries. I have libraries downloaded from Git, and I have to set this new environment variable. Let's see, is there any settings dialog somewhere? So basically, so that I can use the old libraries that I have and use them in this new version. Maybe it's configure paths. So this is the library path that I have, but the problem is that they have changed this. I think it's like KiCad symbol sysdir. So we have to add a new one, and we need to like call it KiCad symbol sysdir, and we set it to the same value, like this. And I think we should be able to. No, sorry, it was like KiCad sys symbol there. Oh god, come on. Let's go back. Close E schema and let's go and configure this path. I have never actually set up this version yet, so I'm doing this as I go along on this live stream. And I've never used this version to create a board. This is version 5 of KiCad. Let's see, edit schematic. Okay. So this should work, I guess. Yes, awesome, but we got an error. Error occurred while loading library valves. Okay. So there was no library called valves. Okay, one of the things I really don't like about how they handle their libraries is that when you add the library in like the list of libraries, if the library doesn't exist, it's going to complain. So it's really stupid. I don't understand why you even have to add all the libraries. I think it should just load all the libraries. Like just load everything. Load all the libraries that you have and be done with it. Like I don't want to add libraries manually. I just want to load everything. So let's see, 5430 TPS, 54360 DDA. Which is exactly the one that we need. So that one was already there. Now I want to check if we have the right chip. So there are different chips, which is, this one is the 54360 DDA. And I want to know what the DDA means. Okay, so DDA seems to be the package. But what other alternatives do we have? We have, so this one is called BQ DDA. So what does BQ mean? Out to BQ. What is auto BQ? Does it even say in the datasheet? Like, okay, maybe we need to open the right datasheet then. Okay, actually we don't care about that one. We only care about this one. This was DDA-R. Does it have like product code description somewhere? Here it says something. Okay, so the only thing I think that differs is the number of chips in a single package. But we don't really care because we are going to buy them like one by one here anyway. So we're going to just say how many we want and we're going to get them. So we can use the DDA-R, that doesn't matter. And in the KiCad we're going to use DDA. Okay, let's go to the example schematic that they provide in this document here. What is this? The device is designed to operate from an input voltage supply between 4.5 and 60 volts. Right, okay. So this is a typical application using this buck converter. Let's copy it in here. I press V to set the value. So this is gonna be, let's see, maybe we use let's see what capacitors we can find that are good capacitors. Let's go back here. Does it say how we design for C1 and C2? or is it just... So we're going to have, in addition to the C1 and C2, we're going to have a 100 microfarad capacitor there, as they're recommended on the power supply page. But I just want to see if they say anything else about those capacitors. Output inductor. Okay. Let's see, to ensure proper operation, this is the minimum input voltage. Okay, so if you want to have 5 volts output, you have to have at least 5.56 volts on the input. That's good to know. Okay, it doesn't seem to say anything about those capacitors. What about R1 and R2? Seriously, does it say anything about R1 and R2 besides this? Okay, this is probably it. So let's see what we have here. I just have to go and do something. Okay. the cold would just not go away. It's so annoying. Okay. So it has R1 and R2 there, and where do we have them on the example schematic? We have them on the enable pin. So this is a different thing. And here these are called R5. So these are going to be used to set the voltage. But what are these? I really don't even know why they put it in that way. Maybe this has something to do with just the voltage on the enable pin, which is probably the case. So let's just see if, let's see the absolute maximum rating on the enable pin, and then try to figure out what they're trying to do there. So the maximum voltage on the enable pin is 8.4 volts. Is there any minimum voltage for it to be enabled? Here, let's see. Enable and UVLO end terminals. Enable threshold voltage. Around 1.2 volts. We could say 1.3 volts. So anything between 1.3 volts and 8.4 volts is gonna enable the regulator. So if we go back here and we see that we have an input voltage up to 60 volts, and this is gonna be let's say around 1/5 of that, so a little bit less than 1/5 of that. So probably what they're trying to do here is to ensure that this pin never goes over 8.4 volts. Bring the calculator here. So let's see. So we have 84.5 is let's see, and then we're gonna do, if I can remember correctly, 5.23 times 84, no, plus 84.5, and then we multiply that by 60. No, this was wrong. What did I do wrong here? Let's see. Oh. 8.34 volts. That's perfect. And what is the minimum? The minimum, they say here, is 8.5. So if we go and multiply this with 8.5, we get 1.18. So this is the minimum voltage to keep the enable pin high. And this is probably, let's see, this is 5 volts. So this is not even, this is not the minimum voltage that is required to drive the regulator and output 5 volts. But because they have to use this voltage divider, and because they want to go from a rather low voltage to 60 volts, this results in a circuit that will power down the output when the input voltage is less than 8.5 volts. So that's kind of the drawback that you have to take into account, that just because it's just to keep the design simple with the resistors here, you end up having an input voltage range that is slightly smaller than the voltage range actually is, because it has to kind of make this pin high. Okay, so our input voltage range is 48 volts as the maximum, but we could go to around 55 volts. So I think we are going to design this as though our maximum, absolute maximum input voltage is 60 volts. which I think is a good idea to kind of have that margin. Let's see. And on the input, we're going to put also surge protection diode, I think. We'll see. We'll see what we're going to do. Let's go and design this. So I was going to look up the capacitors. Let's see. We don't have that many. We have some film capacitors and some aluminum capacitors. And very few SMD components. Like 3. What is this? This is wrong. Something is really wrong here. I should have more capacitors at that voltage. Maybe. Let's see if we perhaps would have to lower our requirements. Okay, so this looks much better. If we go with a 4.7 microfarad capacitor, we can use actually a capacitor that is that comes in a SMD. Let's see, 10 times 4. Which is good. And we also have the option to use the aluminum capacitors. Let's go with a ceramic, and we'll compensate also with a larger one. So this would be 63 volts. I also want to check the temperature range, which is usually pretty wide anyway, but sometimes you can have certain parts that are not designed for the full temperature range. So this is from -55, that's perfectly fine. We're never gonna be in any area which is that cold. Okay. Let's make a list of parts. $6053, that's the package. Let's see. Oh, that's millimeters. We're not using millimeters. We're using inches. So it's 2320. Let's find another capacitor which is gonna be 100 microfarads. Oh, they're huge. They are huge. But we can use one of those on the input because we're gonna have several power supplies. We can just kind of use just one of these capacitors, and then we will just lead the input to all the different power supplies, and that should be enough. What was it? 10 times what? 10 times 10.2, right? Yeah. This one is rated at -40, which is what I'm aiming for actually. So some of them are like -55, but it's just a bonus. Let's see. Let's put this resistors on, and then we're going to find out what this resistor does. $84.5. Come on. Can put it there. And then we're gonna go and see RT clock. I think that was the frequency control. Right. Right, okay. So here's how you calculate this resistor value. We'll just use a standard value, 162. No, wait. When I press G, I can grab the part. It won't let me drag the parts in a more intuitive fashion. Like it should drag those lines with the part, but it doesn't. Okay, so we have feedback and we have the bootstrap pin. Okay, I tell you what, we're gonna use the reference ground, and we can do like this. Do like this, and we can use never mind. I just don't like the way the symbols look. I think this is not the standard ground symbol I would use. So let's see, C4. Selection of the bootstrap capacitor. Right, input capacitor. Why didn't we see this? This is, let's see, 226. Oh, I totally missed this one. This is the input capacitor. This is the capacitors we were putting on the input, but we didn't read this section. Right. Where was that? Let's see. There was this frequency calculation somewhere with the resistor. Where was that? Let's see, let's see, let's see. Okay, so a little bit of an update here. So we need to use a ceramic capacitor there for the small one. And which one did we use? We used, this was a ceramic capacitor, but I just want to double check. Oh, this one is an X7R. That's great. That's awesome. Okay, so this is gonna work fine because we have two capacitors and we have a capacitor that basically is the same one that they have used. Well, it's not the same one, but it's like the same capacitance. Let's calculate the boot capacitor. So Bootstrap is going to be a 0.01 microfarads, which is 100 nanofarads. So which one is this? Let's check the price. Let's see. They're quite expensive, like €1 for a capacitor. That's expensive. We're not going to use a film capacitor, we're going to use a ceramic capacitor. Sorry, did I just say something really stupid? Let's just see what this is. Okay, this is a This is a film capacitor, right? What kind of capacitor is this like? Okay, I'm gonna search for X5R and then we're gonna get the right one. 0.1 microfarads X5R. There we go. Now we have a ceramic capacitors and they're very cheap. This is the ones that we're looking for. So apparently I didn't get those in the previous search, which was very interesting. Okay, but the voltages, right? So this is 10 volts and we need 63 volts. So we need to go in here and we need to set the voltage. So maybe we should choose a voltage that is slightly higher, like 100 volts, because those capacitors don't come in 63 volts, according to what they've got there. And this is even, this is cheaper than the previous 63 volt capacitor, but this is the one that we need. This is X5R. X5R, by the way, means that the capacitor doesn't lose its 10% of its value within a certain temperature range. Like X7R is much better. So when the temperature changes, the capacitor doesn't change the capacitance as much as a lower quality capacitor. So this value basically tells you kind of the quality of the capacitor and how it responds to temperature changes. This is a 0603. That's nice. I'm gonna set the formatting to text, so I don't want to lose the zeros in the beginning there. And the next thing is the diode, which they have chosen this diode for. So we can go back and just search for this diode, see if we can find it. This is a 5 amps Schottky diode. Yeah. Usually when you design such converters, you use a Schottky diode for the diode in the Bootstrap circuit, because Schottky diodes have very low voltage drop, and they're very good in such applications. because also the lower the voltage drop, the smaller the diode has to be, because the voltage drop also determines the power dissipation of the diode. So if you choose a diode that has a high voltage drop and you're gonna like pump a lot of current through it, it's gonna get hotter than a diode with a lower voltage drop. So it's always better to use a diode with a lower voltage drop when high currents are involved. Okay, so let's just use that diode as they've recommended. And oh wait, that one is not available. We'll use this one. Come on. What is the package of this thing? It's an SMC package. See, just want to see how they placed it, like that. Okay, so it goes to the ground and to the SV pin. Put it here. No, actually we'll put it here, because we need that feedback. Okay, so comparator pin. I don't know what I'm not sure what I'm supposed to call this. I'm gonna check it out. So what is this? I remember looking at it before, but I want to check and see what this pin actually does. So it's connected to this circuit here. Interesting. It is an error amplifier output and input to the output switch current comparator. Connect frequency compensation components to this terminal. Okay. Compensation, there we go. There are several methods to design compensation for DC-DC regulators. The method presented here is easy to calculate and ignores the effects of slope compensation that is internal to the device. Since the slope compensation is ignored, the actual crossover frequency will be lower than the crossover frequency used in the calculations. Compensating pole. Okay. So what they're doing here is they are compensating for a possible instability, I guess, in the frequency, depending on the output current and depending on the voltage that we configure as the output voltage. So in terms of frequency response of this regulator, they find out the pole in the frequency response and the zero. So these frequencies are going to be are going to have instability around them. Exactly what this exactly how this happens, I don't know right now, but I think that the best thing we can do right now is just to use the values that they've calculated for their reference design. And the only thing we're going to change is the V out here. Let's see. So that's the only thing we need to change. So I think all the other things are exactly the same. So let's say that this regulator here is going to be a 5-volt regulator, and when we copy this to design the others, like the 6-volt, the 12-volt, and the 19-volt, then we're going to change those values. So this is going to be 5 volts. We're going to have 13K, 6,800 picofarads, and 39 picofarads. And also I want to check the output voltage on this pin. So where's the COM pin? Let's see. Pin configuration, absolute maximum ratings. 3 volts. Okay. Okay, so we don't need the capacitor that has to be like rated at 63 volts there. We can just use a normal one. Let's see. So we go and put a 13K resistor there. Press C and I just put it here. 13K. And then we put 2 capacitors. .39 picofarads. So this is gonna go to ground. And then we have just the feedback pin. And for 5 volts, they already calculated the values here. We're gonna adjust the values for other voltages. And also the inductor, yes. Why did they use 10.2K? That is so non-standard. Let's see. Let's just double check. Voltage feedback resistors. So we can select this resistor. I guess what they did here is that they chose 10.2 because both would be standard values. If they have chosen 10, they would probably get some other value here that would be non-standard. Right. So this is like a 0.1%. Very high precision resistors. We don't need that high precision, but it's cheap. So maybe we should choose that anyway. Okay, let's just go for a standard one. So this one, 10.2K. Okay, I'm not gonna put any packages here. I'm just gonna skip that and put the packages later when we do package assignment. Let's see. Was this the one that we've put there, right? This is KA. Right, okay, good. And then we just need to have 13K. %, but that's 120K. Okay, this is a really weird way of presenting the search results. I've just searched for a 13K resistor and I get like 113K. Okay, so this would be good enough. I guess 5% is good enough for that thing. Like it's not that much. Here we got 1%. Let's go for 1%. It's the same price. Why not? And it was 0603, right? Yeah. Perfect. Then we'll go for this 6800 picofarad capacitor, which is 6.8 nanofarads. Let's go. And that would be 6.3 volts. X7R, that's perfect. What's the price? Let's see. Oh, okay, so that was just one of them. Right. Okay, I don't want that. I want to search for all of them. And we can use, let's see. Okay, so 10 volts is a more common voltage for this capacitance and this size of capacitor, so we'll use that instead, and then we can get really cheap capacitors here. This is X7R. Let's see. And 39 picofarads. And none of them are in the stock. Let's see. This is bad. Okay, let's remove the voltage. Do we have any one of them that is in stock? Let's see. There's only one. Okay. That's a mighty non-standard capacitance, 39 picofarads. Like, there are no capacitors almost that have that. Let's just search for 39 picofarads and let's let's see what we find. Okay, I definitely want SMD, and I want 0603. Do we have that? Yes. Good. And let's order by price. Okay, there we go. 16 volts. This was okay. Let's see, C0G. So this one is, I think C0G is supposed to be better than X7R. We'll double check. Let's see. X and C. Let's see, what is the temperature here? So the temperature is okay. Okay, right. Class 1 and let's see, class, where is X5R? This is class 2. Okay. Okay, so they're better at volumetric efficiency, so they're probably smaller, like X7R should be smaller. Ceramic dielectric is characterized by nonlinear change in capacitance over the temperature range. And the capacitance also depends on applied voltage. So, yeah, so class 1 capacitors are accurate and they are temperature compensating. They offer the most stable voltage, temperature, and to some extent frequency. Okay, sounds good. So let's go with this one. And this would be the 39 picofarad, 16 volts, C0G. Good. And then we go for the resistors here. 523K. %. This is really in stock. 98,000 of them in stock. But is it the cheapest one? No, it's not. So I'm gonna pick the one that has a better price. Let's see if we find something that's like 1% at a better price. Why not this one? You know, this one. Perfect. And then we'll just put it here. $523, 1%, 0603. And this one was 0603 as well. Okay, cool. Now, this one, we'll actually order them as capacitors, resistors, etc. Let's see. Okay, I want to do like this. Insert columns left. And we want to do like this. And we can put this here. So anything else? 10K2, that's there, cool. Okay, so SV is the output, so we can move this a little bit down here. And I'd like to move this one a little bit, like so. Let's see. No, wait, that's bad. Okay, let's delete that one. Move this one here. Okay, cool. There we go. Good. So, and then we need the inductor, and we need a few more components. Output inductor selection. To calculate the minimum value of the output inductor, see equation 28. So the value of output inductor depends on the output voltage and the input voltage and the switching frequency. And then also you have to calculate the current ripple to be able to also then calculate the peak current of the inductor. And this is the current we're going to use when we choose the inductor. So we have to have a 4 amp inductor. Let's see, for this design we have inductor value of 7.3 and the nearest standard value is 8.2. And it is important that the RMS current saturation and current ratings of the inductor not be exceeded. For this design, the RMS inductor current is 3.5 amps and the peak inductor current is 3.97 amps. The chosen inductor is V. Oh, there we go. So we can go and copy this one and we'll see if we can find that inductor. There we go. Okay. And what we can do also here in Mouser, we can actually search for similar components. So, oh, god damn it. Like, the moment I click, the page moves. That is so annoying. Okay, so we can go and pick the inductor inductance and go with the SMD. This is not an SMD inductor. What the hell? This is supposed to be an SMD inductor, but it's clearly a through-hole inductor. Let's see the datasheet. What does the datasheet say about this inductor? Well, the datasheet says this is an SMD inductor. Okay, interesting. But the picture doesn't say that it's an SMD inductor. Let's check what else we can find here. Let's pick some package that is like Okay, these are going to be really small inductors. No. That we're not going to use. Okay. What shall we pick? Let's see. Let's pick something very similar to this one. Let's look at all the inductors that we can find here. So 4.8. Like I'm gonna pick something that they have in stock. For example, this one. What is the current? 4.5 amps. Let's check the landing pattern and okay. Well, this seems to be like a pretty common inductor. Do we have any other ones? Here's the one that we were looking at. 5.05 amps. But they only have like 986 in stock. Like, seriously. This is 4,000 in stock, so this is probably going to be around for longer. Let's see. Okay, so I'm going to pick that inductor. I'm going to go with this one. And this is mount 7.2, right, okay. 7.2 times 7265 times 4, okay. I'm going to double check that landing pattern later. Let's see. 8.2 microhenry. Is that like 4.5 amps? Let's double check. 4.5 amps and 6540. That's good. 6540. A standard package. I always like inductors that come in standard packages. That is just so much easier to work with. Okay, what else do we what else do we have? Let's go back here. Let's go to the reference design. On the reference design, we have the capacitors. 47. Let's see, output capacitors, output voltage, feedback resistors, compensation. Output capacitor. There are three primary considerations for selecting the value of the output capacitor. The output capacitor determines the modulator pole, which is important, the output voltage ripple, and how the regulator responds to a large change in load current. The output capacitor needs to be selected based on the most stringent of these three criteria. The desired response to a large change in a load current is the first criteria. The output capacitor needs to supply the increased load current until the regulator responds to the load step. The regulator does not respond immediately to a large, fast increase in the load current, such as transitioning from no load to full load. The regulator usually needs 2 or more clock cycles for the control loop to sense the change in the output voltage and to adjust the peak switch current in response to the higher load. The output capacitance must be large enough to supply the difference in current for 2 clock cycles. Okay. For example, the transient load response is specified as 4% change in Vout for a load step from 0.875 amps to 2.625 amps. So if the load current rapidly decreases, then there can be a voltage spike, which is usual response even when you work like with motors and stuff, that you get this increase in voltage. So you need to have a capacitor that can absorb that voltage increase. So let's see what they have here. They have a equation for so C out must be more than and then they have the current out. Let's see. Okay. So these equations specify, let's see, this equation 34 specify the minimum capacitance required to deal with the output ripple, and equation 35, let's see, equation 33 calculates the minimum capacitance required to keep the output voltage overshoot to desired value, and we can also calculate the ESR. And we can also calculate the, let's see, capacitors are generally rated for maximum ripple current that can be filtered without degrading capacitor reliability. Okay. And we also get a calculation for the ripple current. So let's see if we can find a capacitor that meets all of this. They have used a capacitor that was, let's see, $5 milliohm of ESR. So ESR has to be less than 27 milliohm. Okay. Let's go and find a capacitor. So they use 2 of 47 microfarads. Okay. 47 microfarads. Let's see. Volts. Let's search for this and see if we can find something that has the right ESR. 10 volts and SMD. Okay, I don't want to have a tantalum capacitor. I want to have something else. Do we have any, let's see, do we have any filtering criteria that can support something else? Like, I don't want to have all of these. I don't want to see all of these. This is ridiculous. Okay. Let's see here. 47 volts. X5R. Let's check this one. So this is an X5R, 47 microfarads, and it is, let's see, rated voltage, termination, temperature characteristics, high voltage, multilayer thickness, packaging, special code, capacitance, tolerance. Okay. It doesn't say much more than that. It doesn't say what ESR they have. Let's see the ripple current. Okay, so this is a 50 milliamps charge-discharge current. Now, if we go back here, we can see, do we have any current here? So, this is clearly a much larger current than we have here. I'm going to change this to SMD components. I only see the SMD versions of the capacitors. And I'm going to set the DC voltage to, let's see, between 10 and 16 volts and SMD. And then we can see what we find. Okay, so these ones are low ESR, 56 microfarads. ESR is 1 ohm. Ripple current 90. So the ripple current that we have here is much larger. So we have a ripple current of 270 milliamps. So our capacitor has to support this ripple current. And if we look at the data sheet of this capacitor, if we pick the 10-volt capacitor, we only support a ripple current of 90 milliamps, which is way too low. The capacitor is just gonna degrade quickly. So we have to pick something else. We have to pick a capacitor that has a larger supported ripple current. Let's see, KR3, large ripple current. Okay, can I actually see the ripple current? Allowable ripple current. Well, we should get good ripple current with these capacitors, but I just, like, is there any specified value for the ripple current, just so that we can know, so we don't just, you know, pick something on a guess or like on a circle that says it has excellent ripple current handling, but can we actually see the ripple current in a table or something? Okay, there we go. So it's in the order of several amps, but we do not see any. Let's see. Okay. It's an X5R capacitor, 47 microfarads. Let's go with this one for now. I'm just gonna sort this after price and just see if I can find something else. Okay, so this one is slightly cheaper. This was the one that we've seen before, which was which had a very low charge discharge current. Okay, let's go with this one. Put two of them. At 47 microfarads and 10 volts, X5R. And they are at 0805 package. So and the inductor, obviously. We picked the inductor. Let's see. So from the diode, from the switch pin, and those come before the sensing, right? So actually, we need to delete that, and we need to go and add the inductor. Okay, I'm gonna delete that too, and delete that and that. And then we're gonna put this capacitor here, and we'll grab this one and move it a little bit down there. Like that. And let's just put this one there, this one there. So I'm not going to use any labels for this net, for the feedback net, because I want to put several of these schematics on the same page, and I don't want to just confuse the different nets. If I name a net and then I copy the schematic, make a copy of this, then I don't want to have to change the net name on the copy. 8.2 microhenry, was that like 4.5 amps? And this one goes there. And then we're gonna put a mounting hole. Let's see. Are there any mounting holes here? Test point. No. Okay. I wonder if we need to add a new library for the test holes. Didn't we have that library? I'm not really sure about the new version 5 of KiCad and how it handles the libraries. I don't just want to add like a PCB component. I want to add the holes on the schematic, and then I want to assign a footprint to them. So I'm just gonna check an earlier schematic that I had. Let's see. So it's supposed to be a mounting hole symbol, which I don't seem to see in this version. Where is that symbol? Okay, so the mounting hole symbol is not available in the current set of libraries. Interesting. Let's see. Can we search? Let's see. If we go to KiCad. So we have library for connectors, so we have, right, mechanical. So that's the library we have to add. That's actually the library we were missing here. If we go to library simple tables, do we have the mechanical? Mechanical, yes, we're supposed to have that library, but what the hell? Let's see. Wait. Okay, so the library that we have on the computer here is named mechanical with a large M. Okay, let's see. Let's see if we find it now. Yeah, there we go. Mounting hole with a pad. Awesome. See, this is what I mean with KiCad's library handling. It should just load all the libraries under wildcard. So the question is, do we actually want to have a mounting hole as the power connector down here? Or do we want to have a pad? I think that probably a pad would be better for this solution actually. Like, if we're gonna use a pad, we can just use a pin connector. Seriously. Oh my god. Do I have to do this with every single library? So is this supposed to be in connectors or where? I don't have them! God damn it! Which library is it in? Okay, let's see. Which library is the con? Huh. Like, no library. Interesting. Do we not have any connector? They're supposed to be called con. Okay, this version of KiCad is not the official release. This is just a build that I made from the Git source of the version 5 of KiCad. So this is clearly not completed. This is not a stable version. Okay, let's see, 01x01. Okay, connector. Can we see if we have connectors here? Oh look, we don't even have that library here. Interesting. Come on. And here they're called like con with lowercase letters after C. Interesting. Anyway, can do like this. What we're gonna do is just connect this pin here. And this is gonna be our 5-volt output from the regulator. And this is gonna be connected to a label. and then we'll just make a little border around it. Okay, excellent. So the only thing here is that I don't want to have this capacitor on the schematic because I'm going to be copying this. So I'll put it outside and then we're going to connect it to VBAT. And ground. Now it came out on the other side. Come on. Let's see. Yeah, that's better, but it still came out on the other side. Come on. This is better. Yeah, that's better. Okay. Then we'll just connect this. And this is pretty much it for this 5-volt regulator, in terms of the schematic at least. In the next videos on this particular subject, I'm gonna be designing the regulators for the other voltages. So we're gonna have power 6 volts and power 12 volts and we are gonna have, let's see, I wonder if we're gonna put any 19-volt regulator here. I think that because the 19-volt regulator is supposed to feed a little microcomputer that is put on the drone, but I don't think it's actually appropriate place to place it here. I'm gonna check my requirements document. I think we'll just do with 6, 5, and 12, and then we'll make sure that these regulators can be stacked so that you can have more of them if you decide to do that. And it's going to be a rather small regulator. We're going to try to cram everything into a very small space. And if another regulator is needed for 19-volt later, then we can design it separately. So I'm going to save this and hope you learned something, and this is it for now. I'm gonna come back with a new video where I will put together the remaining two regulators, and then I'm gonna lay out the board and actually assign all the components which we have picked here. And I'm gonna assign footprints to them, and I'm gonna route the PCB, and then I can show you the completed PCB later. That's it for now.